Hi, sixth graders. Today we are working in Chapter 3, Lesson 2. We are on page 185, and we will be estimating products. The standard that we're working in today is sixth grade in the number system, Standard 3, fluently add, subtract, multiply, and divide multi-digit decimals using the standard algorithm for each operation. And today we are specifically looking at multiplication. Remember the vocabulary term product. Product is the answer to a multiplication problem. So let's look at some estimating. Estimating products is really helpful to us because it helps us to know if our answer is reasonable. So skateboarding. The record for the greatest distance traveled on a skateboard in 24 hours was set in a recent year by James Peters. He traveled about 7.6 miles per hour. Plot 7.6 on the number line. Okay, so anytime we're working on a number line, we want to take a look at where it starts and where it stops. This starts at 7 and finishes at 8. 7.5 is right in the middle. So if I were to kind of estimate this, and I'll get a pencil, 7.6, 7, 8, those are a little big, so then I would downsize a little bit. I left a little bit too much room in between. 7.6, 7, 8, 9, and then 8. So I like to partition it into pieces so I have a better idea. This spacing, this interval is a little bit off, but it's close enough. So I'll go just a little to the right of that one right there. So I'll call that approximately 7.6. What whole number is 7.6 closest to? So obviously it's in between 7 and 8. So we asked 7.5 would be right in the middle. 7.5 would be right in the middle. So 7.6 is closer to 8 than it is to 7. Estimate how many miles James Peters traveled in 24 hours. So we would estimate 8 miles per hour times 24. 24 times 8. 8 times 4 is 32. Write the 2, carry the 3. 8 times 2 is 16, plus 3 is 19. So approximately 192 miles. And then because we rounded, so the next question asks us, is your estimate higher or lower than the actual distance he traveled? And then explain. Well, he was traveling on average 7.6 miles per hour. In our estimate, we rounded the 7.6 up to 8. So we made him faster than he actually was. In our estimate, we made him faster. So our estimate would be higher than the actual distance. Okay, so my estimate is higher than the actual distance. Because I rounded his speed up from 7.6 to 8. All right, next, a new record was set but later by Ted McDonald. He traveled about 10.1 miles per hour for 24 hours. About how much farther did Ted McDonald travel? So he's going 10.1 miles per hour. We will round that to 10. Okay, 10 times 24 is 240. So we would say 240, and again, this is an estimate, minus 192. So I'm not going to do the subtraction algorithm. I'm going to count up. So from 192 to 200 is 8. And from 200 to 240 is 40. So 48. Okay, you can subtract that with the standard algorithm, but personally, I would rather count up to 200. That's 8. And then count up to 240. So that's 40 more, 48. So Ted McDonald traveled about 48 miles farther. All right, so then if we want to think about our thinking, so some metacognition here, which mathematical practices did we use? Persevere with problems. We did have a multi-step problem here at the end. Okay, so we had to keep going. Reason abstractly. These were pretty much straightforward calculations. I don't think there was anything abstract. We're not really working with algebra or solving for unknowns just yet. Constructing an argument. Not really. We're just looking at very basic differences between two numbers. If we had something that was wrong and we had to explain why it was wrong. Oops, I didn't mean to check that. Model with math, we did model with our number line. So that number line helped us to visually see where the 7.6 is and prove that it's closer to 8 than it is to 7 with a visual aid. I think most of you probably didn't need that number line to know that, but we did use it as a model. Our mathematical tool was our number line. We attended to precision. Well, we did in the sense that we were using our estimate to help us, because we'll use estimates to help us to know if our answers are correct. So I'm going to give that a check, even though it doesn't quite hit the box, but it's close because estimating helps us to ensure that that our precise answers are reasonable. Make use of structure. We didn't really have any sort of repeating structure or pattern to continue here. These were each individual problems, and the same thing with using repeated reasoning. We didn't really do that in this problem, but we persevered with our problem. We used a number line for a mathematical model. We used the number line also as a mathematical tool, and we were precise in our reasoning. Okay, so let's turn the page to 186. So we are looking on page 186, estimating products using rounding. To estimate products of decimals, round each number. First, underline the digit to be rounded, then look at the digit to the right of the place being rounded. If the digit is 4 or less, the underlined digit remains the same. If the digit is 5 or greater, add 1 to the underlined digit. So I'm going to argue with this, the underlined digit remains the same. Well, technically it does remain the same, but remember the entire number gets rounded down. Okay, so when we drop off anything that's after that number and keep the number, we actually have rounded the whole number down. The digit does remain the same, but the number itself got smaller. Because like if I had 2.55, that'd be like $2.55. Or let's say 2.54, that'd be $2.54. If I rounded it down to 2.5, now I only have $2.50. So the actual value got smaller. We rounded it down, but the digit, the 5, remained the same. So if the digit is 5 or greater, add 1 to the underlined digit. After rounding, all place values to the right of the underlined digit have a value of 0. After the numbers are rounded, then you multiply. Okay, so if I have 8.7 times 2.8, 8.7 is closest to the whole number 9. 2.8 is closest to the whole number 3. So 9 times 3 would be 27. So the product would be about 27. Example 2. Okay, 42.6, is that closer to 42 or closer to 43? It's closer to 43. 37.2, is that closer to 37 or closer to 38? That's closer to 37. Okay, so we have a 2-digit multiplication. I don't have room here to do my algorithm, so I'm not going to use this this box here. In 6th grade, we don't use calculators for our basic algorithms because you won't be allowed to use it in a couple reasons. And I mean, not just that you're not allowed to use it in the M step, you're not allowed to use it in the M step, but also it just strengthens your overall understanding of math skills. And it's going to help you to be faster when you get to pre-algebra and algebra, so you don't have to break out your calculator for really simple things. So 43 times 37. And you can, if you wish, 6th graders, you can start using a dot for multiplication. You don't have to, but when we get into more pre-algebra, especially in 7th and 8th grade, you will be using a lot more X's in your math, so you may not want to be using the X for multiplication. But in 6th grade, you can. I'm just going to start using the dot, the multiplication dot, just so you kind of get accustomed to seeing it sometimes. I'll use it sometimes and sometimes I won't. 7 times 3 is 21, right? The 1, carry the 2. 7 times 4 is 28. 28 plus 2 is 30. Now I'm moving over here to the next place value over. So remember, I'm going to write that digit here underneath it. 3 times, so this was gone now because that was from what I carried before. 3 times 3 is 9. 3 times 4 is 12. And I add these up, 1, 9, 5, and 1. So 1,591. Okay, so the product is about 1,600. Okay, and actually, I think what they wanted us to do here, I know what they wanted us to do here. was, let's erase this. So that's actually, they wanted us to round these both to 40. That's why 40 times 40. Okay, so let's talk about that estimate. 40 times 40. So I can do the estimate of 4 times 4, which is 16, times 10 times 10. So 16 times 10 is 160. 160 times 10 is 1,600. Okay, so we can do that in our heads. I want to show you that again. So 40 times 40. 4 times 4 is 16, times 10 times 10. 16 times 10 is 160, times 10 again is 1,600. Okay, so the product is about 1,600. I would accept this also, but they were looking for an even more rounded number here, which is why I just realized they did not give us the room for the standard algorithm. Number, example A, B, and C, some additional practice. 9.6, we're going to round that to 10 times 1.8, we're going to round that to 2. 10 times 2 is 20, so approximately 20. And then B, 4.2 times 3.1, we'll round these to 4 times 3, so approximately 12. And then 68.4 times 21.3, so we'll round the 68.4 up to 70. And then the 21.3, we'll round it down to 20. And then instead of doing 70 times 20, where we would need to break out a calculator, so I'm going to regroup my numbers so I can do this in my head. I'm going to write this down. You're going to write this down. Okay, but eventually I hope that you get to the point where you can do this in your head. Okay, so instead of 70, think of it as 7 times 10. And instead of 20, think of it as 2 times 10. And remember, multiplication is commutative. Commutative property means we can do things in any order that we want. This works for multiplication and it works for addition, okay? It doesn't work for subtraction and division. They go in a different order. So when I think of the commutative property, I think of my commute to work and back home every day. So my commute to work is about 12 miles. And then my commute back home, by definition, I'm going from home to work, and then I'm going from work to home. It's also 12 miles. It doesn't matter if I'm going from point A to point B or point B to point A, I'm going the same distance. Commute. Okay, so the commutative property works very much the same way. 2 times 6 is 12, and 6 times 2 is 12. So both of those numbers are 12, have a product of 12. It doesn't matter which one goes first. Okay, so the commutative property lets me do these in any order that I want. So I can think of them as 7 times 2 times 10 times 10. So 7 times 2 times 10 times 10. So 7 times 2 is 14. 14 times 10 is 140. And then 140 times 10 is 1400. So you can do this with mental math. So approximately 1400. 1,400 is the pronunciation. So 1,400 or 1,400, I'm fine with either pronunciation. Okay, page 187. A greyhound can travel 39.3 miles per hour. A greyhound is a type of dog. It's used for racing and makes a wonderful pet. A greyhound can travel 39.3 miles per hour. At this speed, about how far could a greyhound travel in 6.5 hours? Okay, so the 39.3, we can round that to 40. The 6.5, we can round that to 7. So remember, I can do this as a 4 times 10 instead of a 40. So 7 times 4 is 28. 28 times 10 is 280. So the greyhound could travel about 280 miles in 6.5 hours. Number 4. Suppose $1 US is equal to 5.8 Egyptian pounds. About how many Egyptian pounds would you receive for $48.50? Okay, so the 5.8, we're going to round that to 6, and the 48.5, we're going to round that to 50. Okay, 50 times 6, 6 times 0 is 0, 6 times 5 is 30. Okay, or you can do that in your head. 50 times 6, or 50 happening 6 times, is approximately 300. So $48.50 is approximately equal to 300 Egyptian pounds. So let's do some practice problems with the estimation. STEM problems. The Earth is rotating around the sun at about 18.6 miles per second. About how many miles does it travel in 4.8 seconds? Okay, so my 18, I'm going to round, or excuse me, my 18.6, I'm going to round that to 20. And my 4.8, I'll round that to 5. So it will be 20 times 5, which is approximately 100. So that'd be approximately 100 miles in 4.8 seconds. The average walking speed of a person is 4.8 kilometers per hour. Estimate the number of kilometers you could walk in 3 hours. So we'll round this to 5 kilometers per hour times 3 hours. We would go a total of approximately 15 kilometers. Kilometers is abbreviated km, and some people pronounce it kilometers, and that's great too. STEM, a king palm can grow about 2.1 feet per year. Estimate the height of the king palm in yards after 15 years. So in elementary school, we learned about feet and yards. If you didn't learn about it because of the break in education, that's okay. So I'm just going to tell you right now, 1 yard is equal to 3 feet. 1 yard is equal to 3 feet. So we'll get our answer in feet, and then knowing that there are 3 feet in a yard, we'll divide by 3 to find out how many yards it is. Okay, so 2 feet per year approximately times 15 years. 15 years times approximately 2 feet per year will be about 30 feet. And then they didn't ask us for our answer in feet, they asked us for our answer in yards. Well, we know that there are 3 feet in 1 yard. So if I have 30 feet, I just divide that by 3. So 30 divided by 3 will give me 10. So 10 yards. Okay, and if you didn't learn about conversions in elementary school, which you probably didn't, don't worry about it. We'll be practicing more and more and more of these problems all throughout the year, and you don't get tested on these until measurement way at the end of the year. Okay, so we will keep practicing with them though and reminding you about measurement. Okay, let's turn the page to 188. Okay. Okay, example 5. Patrice has $20 to buy 5 binders. Binders cost $4.29 each. Does she have enough money? And explain your reasoning. So we would estimate about $4 per binder. And she has $20. So the actual cost is between $20 and $25. So she actually won't have enough to buy the binder. So let's see here. She only has $20. We rounded this down to $4. So $4 times 5 binders would be $20. And they were not actually $4. They were a little more than $4 each. So she won't quite have enough for 5 binders. She'll only have enough for 4 of her binders. Okay. Let's look at the guided practice. So I'm going to pause the video. Take a look at these practice problems. We'll start off with 1 through 3 and then pause for 4 through 6. So number 1, we have 5.8 times 4. So we will round this 5.8 to 6, and 6 times 4 is 24. So this is approximately 24. 13.92, we will round that to 14. 2.7, we will round that to 3. So let's practice some horizontal multiplication here. So I can carry and regroup with horizontal multiplication too. If this is confusing to you, what I'm about to do, you can always go back to writing it this way. I'm just working on practicing with horizontal multiplication. 3 times 4 is 12. So I'm going to write the 2 here and carry the 1 here. 3 times 1 is 3, plus 1 is 4. So 42. Okay, and if you don't like this or it stresses you out, you don't have to do it this way. Okay, I will do that occasionally, but you can always go back to doing it vertically if you prefer. Number 3, the 94.89, we're going to round that to 90. And the 3.11, we're going to round that to 3. Okay, 9 times 3 is 27, so 90 times 3 is 9 times 3 times 10, or 270. And we always box our answers so that stands out on our work. Okay, while we're doing Canvas for this year, and hopefully continue on to next year, we'll actually type these in, but you will have your work so that we can go over it in class together. We may also try turning these in with pictures, but for now we're going to type in the answers. Number 4, financial literacy. A grocery store sells American cheese for $3.89 per pound. About how much would 1.89 pounds of the cheese cost? And I want to pause right here. We're going to talk about the dollar sign. So you might have some people, so first of all, we're going to round that to $4, okay? And you might have some people who say, well, Lord, I just write my dollar sign after the 4 because I want to, and it doesn't matter. Well, actually, it does matter. So let's talk about why it does matter and why we do want that dollar sign at the beginning. So the same way that we want to start each sentence with a capital letter because it cues us that we're starting a new thought, the same way we want to end each sentence with punctuation, whether that's a period or a question mark or an exclamation mark, so we know there was a definite ending. We want to do the same thing with the dollar sign because it's going to cue the reader how we read the number. So when we read this number, we say $3.89. When we read this number, we say 1.89. So at the beginning of this number, when I'm reading it, I know I'm going to read this decimal point as the word and. And I know I'm going to read this decimal point as soon as I start reading this number as 0.89, or I'll say 1 and 89 hundredths. Okay, so it does matter because, again, this cues the reader that we're going to be talking about dollars and cents. So after the word 3, I'm going to say dollars and. So if I had the dollar sign after, I would be saying $3.89, and that's not how we read our money in the United States. We put the dollar sign first because right here at that decimal point, how am I going to read this decimal point? This decimal point is going to be read dollars and. Okay, so it does matter. We do want to attend to precision here. The dollar sign goes at the beginning of the denomination in the United States. That is how we write our currency. So this is wrong, this is wrong. The dollar sign does go first, and it does matter. So let's erase this. It's painful to look at. Okay, so back to our estimation lesson. A grocery store sells American cheese for $4 per pound. About how much would 1.89 pounds cost? So this we will round to 2 pounds. Okay, so $4 per pound times 2 pounds. 4 times 2, so $8 for those 2 pounds of American cheese. Greg has 52 megabytes left on his MP3 player. He wants to download 7 songs that each use 7.9 megabytes of memory. He estimates that he will need 56 megabytes of memory. Is his estimate reasonable? Explain your reasoning. Okay, so let's see. Yeah, so he estimates that he'll need 56. Is his estimate reasonable? Yeah, his estimate is pretty reasonable. So here we have, so we'll take this 7 songs times the 7.9, we're going to round that to 8. 7 times 8 is 56. Okay, so he needs 56 megabytes. He only has 52 left. His estimate is reasonable, and he won't have enough for all of the songs, so he'll have to leave off one of his songs because he only has 52 megabytes left. Okay, so Greg's answer, or his estimate, is reasonable. Seven songs at approximately 8 megabytes each would need 56 megabytes. And so let's see here if we wanted to be exact. We can multiply that out and see he won't have enough memory there. How do you determine which place value to use when estimating products? So when we're looking at place value, we really want to look at the smaller place value is going to give us a more accurate answer. Okay, so when rounding or when estimating, products, the smaller place value we round to, the more accurate our number will be. I think that's a pretty good answer there. When estimating products, the smaller the place value we round to. So for example, rounding to like the ones place instead of rounding to the hundreds will give us a much more accurate answer of an estimate of an answer. So when rounding product or when estimating products, the smaller the place value we round to, the more accurate our estimate will be. And then in real life also, sometimes you don't have to be, let me get that last line on the camera. Sometimes you don't have to be super precise. So like if I'm rounding, like how much lunch meat do I need to buy from the store? I don't have to be super precise. But if I'm rounding, you know, something for postage and I go over, then I won't be able to mail whatever package that I am mailing. So sometimes, depending on the situation, we do need to be more precise. All right, and that was chapter 3, lesson 2. Thank you so much.